Hello, everyone, and welcome back to your channel, Math Made Easy. Um, I want to start a new course today in probability or probability and statistics, but we'll start with probability as that is the basis. So when we talk about probability, some people think, okay, we are going to roll a die, or okay, it's so boring. But if you come to think about it, everything in your life is probabilistic, meaning that there are many events. In fact, later on, you will see that there are like whole industries that rely on probability to be able to predict the future, health of a corporation or so, money making in all aspects of life. It's not just a matter of, tossing a coin or rolling a die. We start with these because they are simple to understand and to grasp the concepts, and then we build on these. So let's start by discussing the vocab. Every time you learn a new language, you need to know what each term means, how to use them, and so on and so forth. And one in probability, um, okay, since we mentioned probability, there is a historical thing I have to talk to you about. There was um, a Russian mathematician, very well known. He's considered by many to be the father of probability. And probably his friends ask him, can you find a way, since you are good at math, a way to win in our gamblings? And he started thinking about that and laid the foundation for probability. His name was Nikolai Kolmogorov. Kolmogorov. So, Mr. Kolmogorov, it has been reported that before he turned 5, so he was a toddler, before reaching 5, he found that if you add the first n odd numbers, you get n squared. First n odd numbers. What does that mean? It means if you take the first number, odd number is 1, but 1 is 1 square, right? If you take the first two, 1 plus 3, you get 4, which is 2 square. And when you take the first three, 1 plus 3 plus 5, you get 9 or 3 square, and so on and so forth. That's how genius the guy was. Only 5. Anyway, so when we talk about probability, we usually use the term experiment, and some people will say, okay, let me get my, you know, white coat because we are going to the lab. And no, that's not what we mean. When we say experiment, meaning something that has possible outcomes, like tossing the coin. We're back to tossing the coin and rolling the die. So when you toss the coin, you can either get head or tail. If you are unlucky, like one soccer referee years ago in the World Cup, he was tossing the coin and it fell on the grass on its side. Okay, so he had to toss it again. But generally speaking, we say there are outcomes, easy, and usually these are called simple outcomes, either head or a tail. If you roll a die, you can either get 1, 2 through 6. Okay, so these are outcomes or simple outcomes that sometimes we can make it more complex. So for example, I'm going to roll a die. What is the likelihood that I get an even number or a number greater than 3? Okay. So now it's a little not complicated, but it's not, you just don't look at it and say, oh, the answer is this or that. Okay. So we learn experiment, we learn outcomes. Now, usually when we introduce probability theory, we use Venn diagrams because they are easy. Everybody knows what Venn diagram is. So we draw any shape. Usually we draw a rectangle that contains all the possible and none other than the possible outcomes of a particular experiment. So if that was tossing a coin, I can divide it into two equal pieces. I can use a diagonal. I can use a line like that. It doesn't matter as long as the area of each outcome is the same. Of course, we are not going to measure, but we are going to use numbers. So first of all, we refer to that as the sample space. So this whole thing is called the sample space, meaning don't tell me I ran the experiment and get the point here. It's impossible. You have to have something inside. Like again, tossing a coin. I have this is head, this is tail. What else can you get? Nothing. Okay. So that's the sample space. I can divide it into six equal pieces and say this is rolling a die. Or generally speaking, I can have an area here that I call A. That's one event. An outcome here is called an event. So I have an event, and just to make things simple, we are going to say what is the probability of getting something in the sample space if the sample space contains everything? So that's 100%, right? But we usually in probability we use numeric values, real numbers, not percentages. So we say the probability of S equals 1. Okay? Of course, this is trivial, right? So what is the probability that you get something outside of S? It's 0, right? So what's outside? We call it phi, or the empty space. So all the space is here, everything else is empty, including what I wrote here. So the probability of an empty space is 0. And these are the two extremes. You hear it a lot that, oh, it's sure, it's 100,000% true. There's no such thing as more than 100% because 100% is one. So you cannot say, oh, I guarantee it's gonna happen. I'm so sure it's 1,000% happening. And I hear it all the time. There is a 1,000% chance that, well, maybe in where I came from, my country, not here. But anyway, so any probability is a decimal value between 0 and 1. And that's why if you refer to that as area, so I say the area of this rectangle is 1, and the area of this thing, if it's say 0.2, then the probability of A is 0.2. Because you divide by 1, you don't need to say, oh, I have to divide the area of A by the area of S. But because the area of S is always going to be 1, we don't write it. But keep that in mind because we will need it later. Why it seems like some probabilities are hard to find, while if I give it to you like that, it's so easy. We'll talk about that. Okay. What if we include another event? Another event may intersect with A, meaning they are overlapping in some part, or they are like that. If I say this area is 0.2 and this area is 0.1, then the rest of the area is 0.7, right? We know that they have to add up to 1. So now I can easily say the probability of A is 0.2, the probability of B is 0.1, and then we'll see how we refer to the other one. Okay. So let's take it a step further and refer to A and B here. A and B are the word, again, we are learning, remember, we are learning vocab. So we learn few names, we learn experiment, we learn outcome or event, okay? And now we are learning a new extremely important term, are mutually exclusive. Mutually exclusive, meaning they don't have anything to share. Okay? Let's now learn few operators that we'll be using. We are going to use only 3 operators. Okay? Like when you learn like regular arithmetic, we tell you plus mean you add the numbers, minus you are subtracting them, times is multiplying, and this symbol divide is division, right? Pi. Here we are going to learn, so what operators can we use if we have compound events? So the first one, so in the set theory, we use the term union, and we refer to it with this symbol, and that translates in probability into or. And or here, excuse me, is referred to as the logical or or the inclusive or. We'll see what that means in a second. This is exclusive, this is inclusive. Then we have the intersection that translates in probability as and. Okay? And finally, we have, usually we use an apostrophe for the negation or the complement. And that is the not, which has precedence over or an and. So what do we mean by saying the logical or? The logical or is not the linguistic or that we use in our lives. When you go to a restaurant and ask, yeah, unless you are so hungry, they ask you, do you want to start with a soup or a salad? So they expect you to pick one of the or the other. Yeah, you can say, oh, I need both, but that's not the question they ask. They are asking, and most likely if you select both, you will pay for both. But if they ask you soup or salad, do you understand? They only want you to pick one. One is free with the meal, but not two. That is called the exclusive or the linguistic or that we use all in our daily conversation. But this one is the inclusive or. So you either pick soup or you either pick salad or you pick both. These are fine. Okay? So inclusive, meaning you include everything, you include both. Now, if I draw another and not, let's not waste time by drawing a regular rectangle. I'm going to say this is S, and then I have A as before, but maybe larger, and B, but this time they get to intersect. So now notice that here we had 3 areas, here we have 4. Let's say the area of A, all of A is 0.5. And the area of B, all of B, is 0.4. And the intersection between them, this area, is 0.2. So if I come to ask you, what is the probability, the event of and, A and B? So the event is A and B. The probability of that, the probability of A, you can write it and B, or you can write dot and dot B. It's easier to write it like that. Is what? It has, meaning if I'm going to pick randomly a point in this rectangle, so I'm going to close my eye and I have, this is a wall in front of me, and then I'm going to, throw a dart on it. What is the likelihood that it falls both in A and in B at the same time, simultaneously? And you say, where is that? Where is this area that is both in A and in B? This area is in A, but not in B. This in B, not in A. But the one in the middle is both, it's considered as in A because it's inside the green circle or shape or oval, and also in the cyan or pink one. So both in A and B. So now we say the probability of A and B is 0.2. If I ask you what is the probability of A or B. I want the event, the probability of this event, which is the probability of A or B. Notice when I say or, I mean the logical or the inclusive. So either here or in both. Some students may say, oh, it's 0.5 plus 0.4 plus 0.2. That's 1.1. That's more than 100%. What went wrong? Yes, of course, many of you already know, right? You heard it before. And I want to show it to you because there's something. Notice 0.5 is the whole green area, and zero point 0.4 is the whole cyan area. So when you add 0.5 plus 0.4, you had added this area twice, right? Once as part of the green and once as part of the cyan. So you have to subtract it. And you say 0.5 plus zero point 0.4 minus zero point 0.2, which is 0.7. So it becomes the probability of A plus the probability of B minus the probability of A and B. While here, the probability of A or B was 0.2 plus 0.1. They don't share anything, so there is nothing to subtract, right? If I say here, what is the probability of A or B? It's 0.2 plus 0.1 equals 0.3. Here, it's 0.5 plus 0.4 minus 0.2 equals 0.7, which makes the area outside of both to make, if this whole shape has an area of 0.7, of course, not drawn to scale, and the total probability is 1, then outside is 0.3. Okay? Makes sense? Unfortunately, many students think this is exclusive probability because we are subtracting the middle area. No, we subtracted it because it was counted twice, not because it's not part of the event. If you want to make it exclusive or, like the or we use, you have to subtract this area how many times? You got it, 2 times. So I say 0.5 plus zero point 0.4 minus zero point 0.2 minus zero point 0.2, so it's 0.5. Okay? Alrighty. Let's take this thing and on the next page and redraw it. Okay? Same thing exactly. So that we can continue. So this is S. Let's make this bigger because it was like 0.5, even though it's not 0.5. And we have this as 0.4. So I'm going to refer to this area as area number 1, this area as area number 2, this area is area number 3, and that area is area number 4. It turns out that I can name each, using these operators, I can name each area of those. So area number 1, how do you think I'm going to refer to it? Just area number 1. If you say A, no, A is 1 plus 3. If you say A or B, no, it's 1 plus 2 plus 3. If you say A and B, you get only 3. So something is confusing. How do I get this only? Here, you use the not. There is an easy way to say, okay, not meaning anything outside. So this is inside of A and not in B. And the probability of that is 0.5 minus 0.2, right? If it's 0.2 inside, then it's 0.3 outside, so that both of these add up to 0.5. And if this is 0.2, then that also has to be 0.2 because 0.2 plus 0.2 is 0.4. Okay? So area number 1 is A and not B. area number two is B and not A, or not A and B. Area number three, we already know it. We said it's A and B. So what's area number four? The outside. You can say, there are two ways to say it. And you will see now very important theorem that we will introduce. I can refer to area 4 using two ways. In fact, each one of them can be referred to as two ways, but this one is easy because I can say it's not in A and not in B. So not in A and not in B. But I also can say area number 4 is not or in A or B, meaning it's neither in A or B. Notice, or here is the inclusive. So if I say it's not in A or B, I mean not in A, not in B, and not in A and B. So this can be written, which is equivalent as the not is written outside, but it's said first. It's not. It's like you are coming, like, like you do in math, you go the exponent first and then. Okay, so you do not in A or B. A or B is area 1 and 2 and 3, right? That's what we did. So not in that, meaning outside of it. And here we get a very well theorem that you will learn later, but here I'm going to write it in English. And now we are going to transfer probability in English and you will never forget it. How? I'm going to read this as not A and not B, right? We said this symbol is not and this symbol is and. So we are translating the not and the and. Okay? Now, treat the not as a negative sign. If I factor it out, this is crazy, okay? I know that if A is positive and you have a negative sign in front of it, so you have to multiply A by negative, so negative times negative is positive. So I'm going to say this is not not A, right? I took away the not, so I'm left with the A. The not will transform the and into or and the or into and. So the and becomes or and the not B becomes just B because I took the not out. You take the not out, not A and not B. So if I factor the not out, it transforms the not A into A and the not B into B and the and into or. So now when I write it back in set notation, I say not, the not is written outside because it's not applied to A or B. No, it's applied to the whole parentheses. So I have the parentheses out, A or B, which is here. What if I have not A or not B? I'm going to write it as not A or not B. If I factor the not out, the not A becomes A, the or becomes and the not B becomes B. So it's A and B not. Use the not as a negative sign, changing the or into and the and into or. And you can say how I write this or that. Oh, I'm sorry. Oh, I'm sorry. This is B. Oh my God. Many of you were screaming and crying. Hey, are you asleep? This is A prime and B, not B prime. And that happens to me all the time when I talk while writing and I say something and I write something else. I say, oh my God, I'm getting old. Sorry for that. So suppose I want to write this, but this doesn't have not A and not B. Same thing. I'm going to write it as A and not B. I still can factor not out, right? Because as I said earlier, not times not cancel each other. Negative times negative is positive. So that becomes not A, right? And the and becomes or. And when I took the not out, I am left with B. So that becomes not A or B not. And my experience with my students is that when I use the not and the or and factor out as if I'm doing algebra, it becomes much easier than to try to memorize. Because now you know, yeah, not times not cancel each other. So I can factor the not, I transform the and into or and the or into and, the not A into A and the A into not A, and so on and so forth. I hope this clarifies it. We are going to return to that later. Now, some people will say this guy's crazy because he loves Pascal Triangle, so that he always bring it, turn around and try to bring it anyway, even if it's not there. Okay, you got a point. When I say find A or B, we said it's area 1, right? It's area 1 plus area 2 plus area 3, right? This is the A or B. But and then we said, like when we said before, A or B, we said instead of writing it as 1 plus 2 plus 3, I said it's so the probability of that, we said it's the probability of A, remember, just we want to prove that mathematically, so to speak, plus the area of B, and then minus the probability of A and B. See what we did? When we said A, the probability of A, we really added 1 plus 3, right? 1 plus 3. Oops. And then we said the area of B. B is 2 and 3, so plus 2 plus 3. And that's why we had an extra 3. We wanted 1, 2, 3, but we got 1, 2, and 2 threes. So we subtract one area of A and B, and we end up with the correct answer. Now my question to you, what if I have, and I'm going to stop here before we continue next session. Here is my sample space. I have event A, event B, and event C. How many areas will we end up having? Meaning, including what's outside for now. Let's count them. I have this area is 1, which is exclusively in A and not anywhere else. There is this area only in B. There is that area, which is only in C. And then I have the intersection of A1 and 2, I'm sorry, A and B. A and B is this shape, okay? This shape, this particular area, we're gonna call that 4. I can have A and C only, so B is outside and that would be area 5. Then I will have B and C without A. That's area 6. Then I have A, B, and C, which is area 7. And finally, I have something that is not in either one, outside of all, which is area 8. I want to show you something. When we had only, oh, we didn't have one that has only A. So if I only have, excuse me, one event, just one area, how many possible combination I have? I have either in A or not in A. So when I had one event, there were two outcomes, either in A or not in A. When I had two, the maximum I can get is that there is an overlap and we ended up with 1, 2, 3, 4. When we have 3, we ended up with 8. Do you see the pattern? Yes, it's 2 raised to the power of 3. So if I have 4 and there is all possible interactions, I will have 16 outcomes, and so on and so forth. If I have 10, then I may have up to 1024 outcomes. It grows so fast, but it should remind you of something. It reminds you again of Pascal Triangle. When there was no events, so no events. It's an empty space, so there's only one possible outcome, which is no events. When I have 2, I ended up with 2. When I have 3, I'm sorry, when I have 1, I ended up with inside or outside. So they are 2. When I have 2, I ended up with 4. When I have 3, I end up with 8, 2 to the third. And you say, okay, so what? I mean, it's nice, but I don't see the point. I'm going to shock you now. Well, how do I find the probability of A or B or C, assuming that this is A, this is A. I'm not going to write it inside so you think I'm referring only to area 1. And this whole shape is B. And that whole shape is C. So when I ask you, what is the probability of A or B or C? And you say, how can you use the Pascal triangle? Yes. It tells me there is only one way to have no A or B or C in the thing. So it's really meaning the total areas here. I'm not going to worry about that because, again, this is in your answer. How many possible ways you don't get neither A or B or C? So it's outside. There is only one way, which is area 8, by the way. There are 3 ways of getting A or B or C, which is probability of A plus probability of B plus probability of C. Then there are 3 ways you can get 2 together. And this is, I added here, so I'm going to subtract here, and then I'm going to add there. Again, remember that pattern? You add, subtract, add. We did that many times before when we were doing x minus y to the power of n. The first is positive, the second is negative, the third is positive, and even in more advanced, I don't know if you saw this video, is what about expanding sine and cosine of nx, where n is a number, like what is the sine of 4x or the cosine of 7x? You use, again, positive, negative, but that's another topic. You are going to subtract all the possible two ways. So A and B minus A and C minus B and C. And then you add all the possible three ways, meaning all three of them come together. There's only one, which is area 7. So plus probability of A and B and C. And now you can do it for any number of events. Let's see if that makes sense. First of all, let's apply it to the two-way. We added all the possible one-way, which they were two of them, probability of A plus probability of B, and then we subtracted all the possible two ways, which is the probability of A and B. And here we also, you can think of it like we subtracted the probability of no way, which is phi, which is 0, so but it doesn't make any difference. Let me quickly do that, and we call it a day. I'm sorry. Area 1, so probability of A, I'm sorry, is area 1 and 4 and 5 and 7 plus 4 plus 5 plus 7. Probability of B is 2, 4, 6, 7 plus 2 plus 4 plus 6 plus 7. Area C is 3, 5, 6, 7. 3, 5, 6, 7. Okay, then I subtract A and B. A and B is area 4. So I'm going to subtract 4. Then I'm going to subtract A and C, which is area 5. So subtract 5. Then I'm going to subtract B and C, which is area 6. And then I'm going, no, I'm sorry. A and we subtracted A and B. A and B is 4 and 7. And A and C is 5 and 7. We subtracted 5, so we subtract another 7. And then B and C is 6 and 7, right? B and C. So it is in B and it is in C. So we subtract another 7. And then finally we add A and B and C, which is 7. So we end up with a single 1, single 2, 3, 4, 5, 6, and 7. We add everything except 8. Again, when we added 1, they were 4 areas. 1, 4, 5, 7. B is 4 areas. C is 4 areas. But when we did A and B, only A and B, we got really 4, 6, and 7. I forgot to subtract the 7 in the rest, meaning anything that has the letter A and the letter B, regardless of C. So this one has A and B. This one has A and B and C. Also, A and C, anything that has both A and C, it's either 5 or 7. And anything that has B and C, which is either 6 or 7. And so when we do that, all the three 7s will go away. That's why we add an extra 7. And you can do it without checking by using Pascal triangle. So that if they were 4, I will have 4 one-ways, A, B, C, D, 6 two-ways, 6 two-ways, A and B, A and C, A and D, B and C, B and D, and C and D. And then 4 three-ways, A, B, C, A, B, D, B, A, B, C, A, B, C, A, B, D. What did you say? A, C, D, and B, C, D. So there are 4. And then, of course, there is only 1 4-ways, which is A, B, C, and D. So really, you can expand an OR for any number of events using this method. I'm sorry it was very long session, but hopefully I was trying to lay the basis for probability and let you understand the events and the and or and this stuff. Hopefully, I'll see you next time. Have a great day and great time until then. Thank you. Bye.